today I will try to explain this long title, like what I mean by enhanced short time peak in the dynamic susceptibility, and that would be my objective. So if you get the title, then you understand what my work is. So for the last couple of days, there was so many talks around the glasses and active. So I will try to make a bridge around those activity and glass and try to make a connection between them in the dynamic perspective. So for the simplicity, I will break down the whole talk into few simple questions, which we definitely use, like what, why and how. So the what question would be like, what is glass, what is active matter anyway, and what is active glass in general. And after that, why we are observing what we are observing and how we can quantify it to use it further in the observation or any experimental setup. So now, what is glass? So as already it was been discussed by Smarjit yesterday, I will not go into the detail, but some of the crucial point I will mention, because when in biological system recent days, like many of them have mentioned, so there is something called dynamic heterogeneity. Like when people measure, these are certain hallmarks of the glassy system. Like when you see the MSD, if there is a plateau regime due to the caging effect of the dense medium of the disorder system, we see a caging effect. After that, we also see the two-step relaxation of the two-point correlation function. And dynamic heterogeneity is also denote the difference in the slow and fast-moving particle in general. So this is one certain picture of showing what is the glass. This is the famous, like how to create a glass, the process. Like you have to go to lower and lower temperature, and suddenly you will trapped into a glassy medium due to the some local minima of the system. And these are like due to the annealing process, you get different glassy system. Now again, what is active matter? Active matter in general, if you think about, is like when a system of particle, due to their own internal energy, can move in the system, can be considered as an active matter. So this have been shown in like living tissues, and also when like some certain granular matter in experiment vibrated in the disk, in between the disk, it injects certain energy into the system, and this particle shows certain collective behavior due to that motion of the system of particle. So these are some examples which you might recognize previously from certain slides. These are the due to the polarity of the movement of the fish, you see this kind of fish school, and this is the murmuration of Stirling, where the cluster of I will say cluster, so the bird cluster is moving and having some order in the system, like movement has order. And this is the famous epithelial cell molar layer, where it has been shown that the heterogeneity increases when it has been computed due to the movement of the fast moving particle, percentage of particle. And this is the genus particle, which two part has two different chemical reaction with the system and get a kick out of it and have a persistent direction, movement, in certain direction. So what is active glass? So active glass can be considered in two ways. Like one could be like, okay, we know what is glassy system, and we put some active particle which has their own internal energy, can move into the system. Another thing that can be done as like if the active system as a whole can be condensed into a dense medium, that can also thought of as a active glass. So this is one of the earlier paper of showing like if a particle, like Rituparna's paper, like if a particle can be considered as a trapped in a field due to this or neighboring particle, then we can give a Lagrangian equation, and this active force you can see with certain noise has been added directly to the equation of motion, which we also do during the MD simulation. So there are two noise you can notice. One is the thermal noise, another is a thermal noise with some width of tau p, which coming from the persistent time. Now this is the result which we will be needed, that's why I'm showing it again. So this is the MSD, which shows like which shows like there is certain combination which gives the effective activity kind of stuff, and effectively that gives also the temperature kind of quantity if you do in a equilibrium equipartition energy kind of calculation. So this combination is following this MSD as well as Q of T, and they have said like, okay, this effective activity, effective temperature is valid in this quantification. But later it has been shown, like Kalol's paper, like if you do like 4-point correlation, which is a second, fourth order, second fluctuation of QT, then you won't see any overlap, but you see strikingly diverging effect due to the increasing activity. So with increasing activity, you see there is no overlap, and it is the trend is keep increasing, and it has been supported by the theory of some modification of IMCT, which is active IMCT, and that shows this that can capture that trend as well. So it was shown that okay, the effective temperature might be valid to certain degree, but may not be valid in other moment. So yeah. So the model I'm using is 3D combination here with binary mixture, and the activity in the system I have introduced in terms of RTP, random tumble particle, which has certain F naught per particle force. C is the refraction of particle, and tau p is the direction along which the particle movement is persisted. After that time, it will again reassign the direction of the particle, and as a whole, there won't be any net drift due to the activity in the system, so that the system motion is, particle motion is conserved. So system has no drift. So these are some dynamic quantity we are going to measure here, which is 2-point correlation function, which can be defined in terms of simple overlap function, Qt, and chi4. Chi4 is nothing but the fluctuation. It is motivated by some spin glass quantification earlier, where it has been shown that if you consider the fluctuation in Qt, you will get the chi4 like terms, and we are defining it as a dynamic susceptibility, which is also a measurement of heterogeneity in the system. And typically around the tau alpha is when the Qt falls up to like 0.3. So around the tau alpha region, the chi4 gets a peak. So that point people typically denote as a chi4 peak. At least in here it has been denoted that. So yeah, now back to my data and simulations. So what I have done here is like I have considered like system of particle ranging from 400 to 100,000 and changed the system size, and I have changed the activity force and concentration. If you remember, the Kalol's paper only has change in F naught. So if you change the concentration also, it has been not analyzed fully, but here it has been shown like if you change the activity also, there would be change in chi4. So what I have done is like by plotting and taking some kind of interpolation like VFT like, we got a overlap of Qt, which is corresponding to some temperature and activity combination gives us a similar tau alpha. So this is like last system size. What we have done is like 1,000 and 100,000. You can see here like the 2-point correlation and their corresponding chi4 peak is there. And around the small time, you can see there is a peak. So we are going to focus, as my title suggests, in the short time here, and we are going to focus into that, and we are going to change the probing length here to get a better amplification and to observe for smaller system as well. So we will change the probing length to 0.18, and we can see there is, by changing F naught for a fixed amount of tau alpha, there is a certain trend with increasing activity when we are changing the F naught, and we can see the similar change when we change the concentration as well. So the trend is valid for both F naught and C at the short time itself. So we don't have to go to longer time to see this effect. We can capture this effect in the short time as well. So now you can see there is a certain trend when we change the activity. Here we have couple of parameters in hand to check with. So what we can do is like we can change the system size and see what is happening, and we can also fix the system size and change the activity as well. So first two slides what we have done is like for the passive system, if we change the system size, there is a increase in activity, but there is as well as shift in the time scale as well. And when we do this is 2.5 activity, large activity for my simulation. So you can see that trend of shifting time scale is also there, but if you see the scale, it is of the order of 45 or something. So it is 10 times more than the passive case. At the short time scale, you can see the increase. Now you can fix the system size and change the activity. For changing the F0, you can see there is a certain trend, but there is no detectable shift in the peak time scale. And for this is for 10,000, this is for 100,000. So both the systems shows similar effect where there is no shift in the time scale when we change the activity. So it would be useful because for a certain system when we do experiment, if the time scale is not changing, then we would be sure like the system is same, but only the activity is changing, so we can probe that system in that sense and get the activity out of it. So next question is why this peak is appear. So I will do certain quantification to show why that is appearing. So here we have done like cage relative quantity. It was like, if you think like the flocking and so, like an example, what they have done, like it has been the dynamics follow, it doesn't, one particle doesn't care about the whole system, it only care about its nearest neighbor. If they are not colliding, the whole system will sustain. So if we just negate that neighboring effect, then we will get this thing. And here you can see, like when we do the cage relative effect or the center of mass frame calculation, then there is no peak, or you can say it is suppressed, but there is no detectable peak. So one thing we can say from that analogy, that this peak is appearing or has a strong influence of the collective motion of the system, which is also influencing more and more with the increase of activity as well. Now from the shifting part, what we can see is like when we changing the system size for any activity, even in passive case, which Smarajit also earlier shown in other paper, that with changing system size, the peak time scale shifts. And if we compute all the peak and put it together in one place, we can see there for certain F0 and C, there is statistically falling on a same line. So we are going to argue it as like this is following a linear dispersion relation like a phonon in a medium. So it is like omega equal to ck, and if 2 pi by L and 2 pi by T, so it is in this region, at least statistically it is linear in nature. So from these two arguments, we are going to say that there is certain intrinsically certain collective behavior in the system which has a phonon-like features or long wavelength features. So next we have done like put all of the activity together and see what is the system size effect, or is it any system size effect or not. By changing what we have done, another thing is like if it is true for canonical and grand canonical, what Smarajit also told yesterday, grand canonical here we have calculated in terms of block analysis. Block analysis you can think of as you are allowing the fluctuation in the boundary. So it can be considered as a grand canonical ensemble. So here you can see like this is the block one and this is just L by 4, which is just 4 block average. So you can see the trend, there is a trend of certain saturation, not much, but it is not diverging that much. So you can see it is valid for canonical as well as grand canonical as well. And after that, we have done the scaling analysis by displacement correlation and use that scaling to fit into a master curve. And we see, at least in our simulation data, it is overlapping quite nicely. And this is the increase of scaling for different activity. Here you might notice, like, we have already started to consider C F naught square, because when we change the activity and C and F naught, that combination starts to hold. So this is we are going to use this, we are going to use this relation, like length scale is growing proportional to the effective activity, and consider the chi4 peak has the influence of activity, also the system size effect, and decoupled it, and with a little bit of algebra, when the system length scale is system spanning, we can get this kind of form, which has been used in this effective activity calculation. Effective activity has been proposed here first. So at least in our result, we can decouple the activity effect and get this equation, and we can see, like, when we separately put F naught influence and C influence all together, you can see there is certain trend in it. This is a combination of different F naught and C. They also fall under certain function. So from this, we can surely say that there is certain function inherent to the system, which has a combination of C F naught square. We have fixed, at least up to this case, the tau p fixed, but it is holding to this scale, and this is true for canonical as well as grand canonical as well. So my takeaway point would be, like, when in many systems, like now people are interested in measuring heterogeneity and all. So if there is any fluctuation in some short time scale, so they should not consider it to be a noise and measure it carefully, so they can get more information out of it. And there is a certain combination of effective activity holes which is still there even at the short time scale, and that short time scale effect has a phonon-like behavior. And another thing I would like to mention here, like right now I'm working on like 2D, and this 2D also has this diverging effect, but in much larger scale. You can see for different tau p, for smaller tau p, for changing concentration, the diverging is also there, but after certain time, even when the tau alpha is going down, the peak height is increasing. This has been reported in different experimental setup, but the thing is, we are right now thinking like if they are considering that Marvin-Wagner effect or not. So we are right now studying this thing more carefully. After that, we can say in detail. So this is the conclusion, and this is the paper I just presented. Thank you.
We have time for a couple of short questions. Can I ask one quick question? So you're scaling of the time scale with system size. That just means you're looking at excitation of phonons on the system size scale?
Yeah, we are thinking it as a system spanning. So if it is system spanning, then for different system size, it will get different time scale, and it is showing proportional up to certain, at least up to our simulation data.
And can you try and break down your chi4 into contributions from different phonons? Or?
Different phonons.
Can you like isolate the contributions from the different phonons in your chi4?
Are you talking about the function we have considered, like for the passive on top of active? That one you are saying?
That wasn't what I meant, but
this one?
Lunch.
Yeah, maybe.
The question was whether one can decompose the chi4 into different contributions
this
from
one,
different phonons.
We have considered it, but that can be done or not, that was your question.
Yeah.
So for now we have considered it in that decoupling thing, and after that we have shown that it is showing certain this one showing good